Yeah, hello everyone. So today I'm going to talk about the consensus changes, the execution changes, and the finality changes I talked on the main stage yesterday, and how actually we are going to achieve that 1 second block time and a very, very short transaction time to finality. So, my presentation is structured in two parts. So first, I'm going to speak about the consensus and execution changes, and afterwards about finality. To better understand the steps we are taking in reaching that 1 second block times, we should first look over the initial model and how we upgraded and how we will be upgrading the consensus and execution to reach those goals. So for the initial consensus model, this is what we started the mainnet with. If we look at the blockchain, MultiversX blockchain, the timeline is split into epochs, where each epoch lasts for approximately 1 day. And then we have smaller time units, the rounds. Each round 6 seconds. This gives a total of 14,400 rounds in one epoch. And now looking deeper, like the going deeper into one round internals and see what is happening there during the execution of a block and how consensus is reached on that. So this is the initial model where we have a randomly sampled consensus group. We have different sizes for consensus groups right now. On the shards, we have 63 members in the consensus. On the meta chain, we have 400 out of the 400 eligible nodes. And the way consensus happens and the execution happens is that among these consensus group members, there is one member, which is the block producer or the block proposer. And the other ones are validators in the consensus and need to vote on the proposal that the initial validator presents. So the block producer will select a bunch of transactions that he has available in the transaction pool. Of course, he verifies that all of those can be executed. And he will actually try to execute each and every single one in a predefined order. And this comes because we've added, let's say, a protection mechanism. It's more like a higher barrier for whoever wants to front-run transactions. So we have that built into the execution model. So after he executes in this predetermined order the transactions, then he reaches a result for the entire execution. He puts that on the block, on the proposed block, and then he tries to send this block to the other consensus members. Here in the diagram, there's a direct dotted line connection between the block producer and the other validators, but this is not exactly how the block gets propagated. So if you know how the gossip works, you might know that the block gets propagated from node to node to node until it reaches all the intended audience. So simplifying this, after the block gets propagated to all consensus group members, these consensus group members used to start from that point and to process exactly in the same order with the exactly same rules that the block proposer or block producer used, and reach a result, then compare it with whatever the block producer has reached. And if these results match, everything was okay, all the rules have been satisfied, then they must agree with the block. Of course, if the validators are honest, they will present their vote, which means they will sign. They will use a BLS signature to show their voting on this block. They will propagate again through the network their vote, and these votes will finally, eventually, reach the leader, which is the block producer, the consensus leader. And here, the leader was responsible for aggregating all these votes, counting the votes, seeing that enough members of the consensus have reached agreement on this block. And then, if all rules again are satisfied, present the final block data, which means that it aggregates the signatures, puts that on the block, and then the block gets finalized, and he sends the final data to all the consensus members, and not only the consensus members, the entire shard, and also, in our case, also on the meta chain, because meta chain needs to know that the shard has reached a consensus over one block. Of course, you can see here there were some issues. It was not very efficient. So if you look closer, what happens is that the block producer executes, then he needs to wait while the other consensus group members execute as well. So everything is serialized between the block producer and the other consensus validators. Now, we go to integrating the scheduled transactions. This happened last year. And what we try to solve with that is remove a bit of the wait time and do some more processing in that spare time. So how the previous model was upgraded was that besides the first part where the block producer executes transactions, he also selects another set of transactions in equal amount of gas to the previous batch. He will pre-validate everything, ensure that these look like valid transactions, the accounts have enough balance, and these transactions could be executed. But he does not execute them at this point, propagates the block, and then he tries to execute the second batch in parallel with the other consensus group members. This means that we managed to double the amount of transactions being executed during one consensus round. Of course, the validators in the consensus will follow the same process. Will first execute the first batch for which they already have a result. They will agree that the second batch looks correct, and they will agree that they will start processing it afterwards. So they will vote on this, send their votes, which are the BLS signatures, and then the block producer will aggregate these signatures and send the final block data. Now, there is another problem with this model, but I will go to that later. We tried to, since we've seen in production that this model also works with the scheduled transactions, we came up with an improved model, where consensus and execution v2, we try to execute everything on the model of scheduled transactions. So we reduce a lot the first part in the round, where the block producer simply selects the transactions from the pool, pre-verifies everything but does not execute, proposes this batch of transaction, and then in parallel with the others in consensus, they try to execute. So we leave more time for execution, being able such to increase the throughput again, because more things happen in parallel. Then everyone agrees on a final result. Of course, they need to agree in the sense that while providing their signature, they also provide the final results they reached. And if the block producer has a majority, more than 2/3 plus 1, that agreed on the same result, then the old process happens. He aggregates the signature on that final result and propagates it to the network and the meta chain. Now there is one problem you might have noticed, or maybe it's not visible in this diagram. What happens with the final state? So in the previous model, the state of the scheduled transaction, so what result for the state transition we got after executing the scheduled transaction, these were not part of the consensus. So we had to move the result on the follow-up block. This meant that even though we managed to execute more transactions in the same amount of time, the finality for those scheduled transactions were delayed with another block. With the consensus and execution model V2, as each one of the consensus group members gives also the final result on the same round, we can reach consensus at the same time on the same data. So we gain again one block reduction on the finality of the state transition. But there is again one problem with this model as well, or at least one problem. How do we solve the overestimations in gas on transactions? If the block producer only selects transactions and does not execute them, then he has no way of knowing the actual gas usage. So executing with this model, we might end up having a lower throughput than before. So how do we overcome the overestimation in the transactions? Well, we overestimate also in the proposal. So we try to fit much more gas that could be allowed in one block time, but add some rules on when we should provide our proofs for consensus. So we have some predefined gas-used checkpoints where each of the consensus group members needs to snapshot when he does the execution and provide signatures for those, but then send them at the end whenever they reach the time limit for them giving their results. So there may be multiple such checkpoints. Currently, I think we're designing for 2. Also, currently we have some penalty on the mainnet, where if you overestimate with much more than 10 times the gas for one transaction, then your gas is being taken. So in order to reduce a bit the overestimation, also for the transactions and also for the blocks, we thought it was safe to reduce this overestimation penalty to more than 4 times instead of more than 10 times. And then we can work with also smaller sized block proposals. And then, the same as the previous model, consensus is reached on the latest checkpoint that has reached consensus, or the 2/3 plus 1 out of the consensus group members agreeing on the same state. But there is another problem, which was there since the beginning. We see that we have a single point of failure, actually, in this whole process. After the block gets proposed and everyone reaches agreement, we still depend, in this model, on the block producer sending the final data and producing the final aggregation on which everyone will agree. How can we remove the block producer as a single point of failure? Or let's see first what would be the problems with this design. Well, it can add equivocation during consensus. So you can end up with multiple blocks if he withholds sending the final data, and then another block producer creates another block for the same height, and then we will have 2 blocks with the same height in the network, each of those having reached consensus. Which one is right? Until now, we have solved this by a confirmation block, but we can do better. So we are removing also the consensus, the proposer as a single point of failure, with the addition of equivalent consensus proofs. What are these? This means that any node that has participated in consensus, as I mentioned earlier, the messages get propagated to the entire shard, the signature messages, so every single node has a view of whoever signed. So they can do the aggregation themselves. Why should we limit ourselves to the proposal that was given by the leader. So we empower every single node. Even nodes outside of consensus could do that. But let's say we empower every single node in consensus to send such a confirmation proof, because they can aggregate. And furthermore, we can remove also the proposal signatures as a mandatory requirement. If we have an agreement among 2/3 plus 1, it means there's a consensus. We don't need specifically the block proposer's signature on the final proof. And also, what we used before the proposer signatures on the final proof was to make sure that the original proposal was being run through consensus. But if we're looking at assumptions for PBFT, we already assume that 2/3 plus 1, at least, are honest. So we should definitely agree then that the proposal was coming from an honest, or the proposal that has reached consensus was the correct one, right? If 2/3 plus 1 have reached consensus. But there are problems also with this one, and I'm going to talk about how we can overcome this in the implementation. So if we allow equivalent proofs to be propagated, what do we do with the high traffic that this could generate? Imagine for metachain, we need 267 out of 400 signatures to say that consensus was reached. But now if we take combinations of 400 taken 267, we get to a huge number. This is, just to have an idea, it's on the level, on the order of 10 to the power of 109. So we could have that amount of messages being sent through the network, and imagine the load that those could generate. So in order to solve this, we change a bit the way messages are being accepted by validators or by nodes in the network and being propagated further. So each node will become a traffic limiter as well, where if he already sent one equivalent proof, he will not need to send another one. One equivalent proof was sufficient, everything is fine, consensus was reached, everyone is happy. We do not need to flood the network. Also, another point with this is that even though, for example, you are acting as a traffic limiter, it doesn't mean that others are acting like that as well. Of course, we are depending on the majority to be honest and follow the protocol. But what if you receive a lot of messages that are flooding you? One of the big problems here is that verifying these signatures, so the votes, or the proofs in this case, is costly. With BLS signatures, it is a bit costly. Of course, BLS signatures have their advantages, and this is why we're using them, but on the CPU, they are costly. So we don't even need to verify them. Why would we if we already sent a valid proof, right? So this is how we solve also the CPU load. I mentioned about the proposer signature not being requested, but how then we prove that we have reached consensus if this proof is not on the block? Because this way we are removing also the proof from the block. So it goes together, like they are in a single consensus message or propagated message through the network, but the signature or the proof is not yet part of the block, but it travels with it. So it goes in the same package to the metachain, and if metachain or whatever other node in the network has received one such construction of a block, a proposed block, and its associated proof, then everything is fine, right? The proof still needs to be on the chain, because for anyone coming new to the network who has not observed personally that consensus was reached and the proofs were propagated and validated, we still need them on the chain. But we can move this step, the proof, to be on the next block. Yeah, so this concludes the changes on the execution model and the consensus part. And now, going further towards finality, you will see some of the changes I mentioned will also allow us to improve the finality. And to understand why we had 6 seconds blocks in the initial design, I will go a bit through the initial constraints. We had to set 6-second block times because of several reasons. One, we needed to ensure that in these 6 seconds, the block that has reached consensus was propagated to the majority of the nodes in the shard, if the intended audience for the consensus was the shard, or the entire network, or shard plus meta chain if this is the finalized data. And propagation, as I mentioned, would take time. We have latencies, maximum latencies we need to accept so that we know that it's predictable if my machine and my setup can be a validator. We need to accept some latency, maximum latency constraints. And then, as I mentioned, you do have some hops in the message propagation we need to account for each of the consensus communication rounds that happen during the consensus. And then we also have some constraints on how long it takes to do miscellaneous jobs that do not necessarily relate to transaction execution. And I would say there, like the verification of each individual vote, or the verification of the aggregated vote, or the creation of the aggregated vote, which all eat up from the round time, and we need to account for. And then another part, so this time for 6 seconds, what I didn't mention is that not only the communication, for example, the first rounding of communication inside the consensus, where the block proposer sends the block, that's not the only limitation here, because the other nodes might not have the data for the block that was proposed. They will need to synchronize that data. Transactions they may not have in their transaction pool, they may need to request it, and it takes time to send the request, receive the data. So there are multiple reasons here, and also through simulation to find out that the messages get propagated to the entirety of the shard or shard plus meta chain in this time would be sufficient. So this is why we decided for the 6-second block time. Now, also affecting finality, we also had one confirmation block on the shard execution, on the execution shard, and we also had one confirmation block on the meta chain. I will get on to the reasons why we had those further down. Now, laying the foundations for advancements. The first step we wanted to do was, how can we increase the execution time in the block by removing as much as possible for what I called earlier as miscellaneous stuff. So we tried to redesign the signature aggregation, and we did this for one reason. Initially, when we designed the vote aggregation method, we needed to add some protection against one specific attack vector, which was rogue key attacks, rogue public key attacks. What happens with rogue public key attacks on the BLS aggregation signature or aggregation scheme is that one malicious, let's say, user could register a public key that is such constructed that it can also provide votes for multiple members that have already registered, if we do not add this protection. So instead of one node, one vote, we would have one node, multiple votes. And this is why we initially had the protection for this type of attack vector inside the signature aggregation scheme itself. But this led to an increase in the verification time and the aggregation time. And just to have an idea on how long it took, it was around 250 milliseconds, I think, when we started on the verification, and around 100 or more milliseconds on the aggregation of 400, so for MetaChain. Of course, for MetaChain, it was not a big problem because MetaChain mostly did notarization, so it had enough time to do this. And this was also one of the reasons we decided for smaller consensus groups inside the shard, so that we allocate more time for the execution instead of this miscellaneous stuff. Of course, this decision came with some consequences, which meant that we delayed the finality of the transactions by adding another confirmation block there. Now, for this aggregation time that took a lot, we also had another protection mechanism, which somehow was redundant with what we embedded in the signature scheme. And that is called knowledge of secret key. That's where the abbreviation comes from. Knowledge of secret key. But we already had that in the registering of new nodes to the system. Every time you register a validator to the system, you need to prove that you have knowledge of the associated private key for that public key that you are registering by providing a valid signature over a message which is unique for that registration. So we had two methods that were preventing the same type of attacks, and we removed this one, and thus gaining 61% aggregation optimization time and 97% verification optimization time. So we removed a lot on part of the miscellaneous stuff, but we can do also even more. And what I mentioned earlier and this thing I'm mentioning now are already implemented. We can optimize signature shares verification as well. So if we look at the MetaChain, and there are, or we can expect 400 signatures regularly for the consensus. If we take the time to verify all of them, like if you have a single CPU, then the time, and you respect the minimum requirements, let's say on a minimum requirements machine, you would get 1.5 millisecond verification time for each single share, which leads us to 600 millisecond single CPU time for the verification of the entire set of votes. And this is what we had until recently. So how can you improve that? We decided to optimistically aggregate all the shares, signature shares, and then instead of verifying each single share, we do the verification of the aggregated signature, which, if it verifies, it will prove that all individual signature shares were valid. And this means that we traded 600 milliseconds with 2 milliseconds, which it takes now after the optimizations to verify the aggregated signature of 400. And if not, if there was a misbehaving node which sent an invalid signature, then the aggregation signature verification will fail, and we added an extra cost of 2 milliseconds. Because we will fall back to the verification of each individual signature, we will find out the misbehaving node or nodes, and then we penalize them. We have implemented penalty for these nodes which get jailed eventually. So the cost for this, it's, I would say, it is not worth it to sign wrongly. So I am expecting that we will actually, every single round, gain the 600 millisecond optimization. Further, now that we have optimized all these things that prevented us to have 400 validators in the consensus group on each single shard. Now we can extend the consensus to 400. Why not? The 63 before, so if we had two consensus groups, consecutive consensus groups of 63 out of 400 that have signed one block that's connected to the previous one, if we compute the probability of the acceptance of the first block by at least 2/3 plus 1 of the shard, which was what we had to ensure before having MetaChain authorize this, the probability of this was 81%, or a bit more than 81%, which we said, okay, it is sufficient for this. And in this case, the MetaChain would be able to start notarizing the first confirmed block in the shard. But now, by increasing it to 100, to the entire set of validators, 400, it means that we actually increase the probability of acceptance by at least 2/3 plus 1, from 81% to 100%. So we no longer would need the confirmation block. This is in preparation for removing that. This increase in the consensus size will also allow us to have simpler proofs, cross-chain, that consensus has been reached. Of course, we need to do another change here, because in our randomly sampling method of consensus nodes, the nodes also changed their position for the signature aggregation. But this does not make much sense, because anyway, you have the same group. You can use any order. If they sign, it means we have approval. So we will change also from the shuffling of the order inside the consensus group to the same specific order during the entire epoch for aggregating signatures in each consensus group. And this means that we can provide commitments to the entire set of 400 members of the consensus group during the entire epoch. We can provide a single commitment to that on the cross-chain, on the chain that we want to do interactions with. And this will allow us to verify proofs of consensus for any type of data we want to prove that consensus was reached. And this type of commitment message, it's a string of 48 bytes, so it's efficient enough, I would say. One day, one commitment. It's very nice. Now, moving further with what was our original intention for all the optimizations we've done, we can remove the shard confirmation block, finally. And now, by removing this, we get a 25% optimization of the both intra-shard and cross-shard transaction time to finality. Of course, there are changes that needed to be done, such as adapt the fork detector and the fork choice rules, because now we don't need to take care of having a separate view of the chain with all the different forks that have been created and decide which one is the canonical path. It is much simpler now, since we have agreement on each block that the network or the entire shard has agreed on that. And with the equivalent proofs as well, we have like almost nil chances that blocks will be reverted if we have the agreement. Then it becomes also much simpler to design the fork detector and the choice, because there's no choice, it's a single one. Okay, I think, one second. Yeah, I'm missing one slide. Sorry for that. So the same thing that we have done to the execution shards by removing the confirmation block. Initially, we did not have a solution for this, but we can do the same for the meta chain. Now, you might think, if we had 400 nodes in the meta chain in consensus, why would we need a confirmation block on the meta chain? We have consensus, right? Well, the original reason was to prevent state reverts on the shard chains. And since we have the potential of malicious block proposers withholding the block before and sending it afterwards and causing equivocation, we had to have some protection against that. But now with the equivalent consensus proofs, we no longer need that, so we can remove it. And this, again, will speed up transactions in the same amount, or if we look at the incremental speed up of transaction time to finality, it would be 33%. But altogether, it means that we halved already the transaction time to finality. And now we have early block proposals. As I mentioned earlier, one of the time-consuming tasks we had to do at the beginning of the round, of the consensus round, was propagating the block, then the nodes requiring their missing data in order to start the actual execution, right? So if we are able to remove this part, then we can have more spare time, either for execution or for further reducing the block time. And in this case, we chose to reduce the block time further. And we managed to do the early block proposals using the same equivalent proofs. What happens now is that one consensus round decides also in some way, or decides definitely, which is the configuration or which is the leader for the next consensus group. Because each leader adds to its proposal the next random seed that will be used to sample the consensus group, or was used before to sample the consensus group, and now it will simply be used to sample the producer, the block producer. So after the initial propagation of the proposal, that information is already available. Who will be the next leader? We can compute it, and that leader can start preparing the next block. As I mentioned before, we changed the consensus and execution model to first select the transactions that can be executed, propagate those, and then execute. So the leader doesn't need to execute on top of the result, the previous result. He just needs to select valid transactions that can be executed. And we also have consensus proofs that arrive much earlier than before, because anyone in the network can start propagating consensus proofs. Of course, for that, we also have some mechanisms to further reduce, besides each node being traffic limiter inside the consensus. We also have a designated order of sending the block information, the block proofs. So we have the information of who is the next leader. We can simply select valid transactions from the pool and create a block, and we can wait for the proof that the previous consensus was reached, which comes much earlier now. And with that information, we already have the data, we can start propagating it, right? And we are using the previous round to propagate the next block, so it becomes ready whenever the next round starts. And then everyone can start directly to execute. And again, this one will allow us to further reduce the block time. Now, the first step, which is like going to be on the safe side, we're reducing first to 3 seconds. Of course, we need to adjust the sub-rounds inside the consensus, how much time we need to allocate for execution, how much time we need to allocate for signatures propagation, and so on. But eventually, these are simple changes, configuration changes. Then we also need to decide on how much gas per block we need to allocate, because now we're reducing from 6 seconds to 3 seconds. Of course, with all the previous optimizations that I mentioned, compared to the version we have right now on the mainnet, probably for 3 seconds we will not have any impact on the throughput. And very important, it doesn't need to change anything on the economics part. So the rewards of our validators stay the same. We just need to configure more rounds, double the rounds inside one epoch, and then everything adjusts by design. And of course, I didn't even mention the parallel processing at the node level, which will allow us to pack even more transactions inside even shorter block times. So actually, eventually, when we reach 1 second, our expectations is that we will reach far more throughput than what we have now with 6 seconds blocks. And this is why I mentioned yesterday on the stage that we target 100,000 plus transactions per second with 1 second block. So what I want you to take away from this presentation is that we have been working on a more efficient consensus and execution model. We already have part of it working with the sovereign chains. You will see a demo afterwards. We are less likely to miss blocks, so we are practically eliminating the state revert reasons. We have much faster time for transactions finality. 1 second block times are in sight. We can target those. And it will have not even, I would say, little impact on maximum throughput, but with the addition of parallel processing at the node level, we will actually have an increase on the throughput compared to what we have now. Yeah, I think this was my presentation. Now, if you guys have any questions, I would be happy to answer.